Hello everyone. So we're now getting a little bit more comfortable with the logistic perceptron, and we saw that it works well if the data is linearly separable, but not all data is linearly separable. However, we can use the logistic perceptron as a building block for arbitrarily more complicated function spaces called fully connected feed-forward neural networks. The reason they're called neural networks is because an analogy that we could make between the form of the perceptron and a neuron. It's not really how our brains work, but there is a nice visual analogy I can make here. So just to recall real quick the way the logistic perceptron works, it's actually a bit like a dot product. Well, it actually is exactly a dot product between a bunch of weights, A, and a bunch of indices, values at indices of an input X, plus some bias B, then fed into some, in this case, logistic function. We will generalize that in a moment. But yeah, it's just a dot product with an input plus some bias, and then fed to that. Well, you can actually visualize this as a little neuron here. So let me show you what I mean. So you could think of a logistic perceptron as a neuron, which has some inputs coming into it. And so I'll draw maybe just 3 here as an example. So let's say that we have 3 inputs, an X that has 3 elements, or an array of length 3. And so each of those elements is going to be an input that's fed into this neuron. So we got x0, x1, x2. And then each of those elements is going to be multiplied by a weight, right? That's what the dot product is doing. So this one's A0 here, this one's A1, this one's A2. And then also we're going to add in this bias. So I'll depict that here by just a little line coming into it from the bottom. So inside the neuron, I'm going to draw a picture of the threshold activation function that I'm using. So in this case, it's going to be the logistic function. And so that is going to depict what happens when I send a particular input into this, and what output I'm going to get. And then the output is going to be drawn just as a little line coming out of this. So we could call this Y perhaps. So anyway, yeah, everything that I wrote down here in an equation can be depicted visually by this neuron. Okay. But yeah, of course, just to remind us that, you know, this can't deal with all kinds of problems like this one, where I have all of my negative examples in a disk within a disk of radius 1, and all the positive examples are actually outside of that. I'm not going to be able to find a single line that does it. Okay, and we understand that a logistic perceptron is just finding a line. However, if I allow myself to use more than one line, I can do this. So let me explain. You know, I have all the parameters for a particular logistic perceptron. Let me actually create additional logistic perceptrons, and what I'll do is I'll store the weights in a matrix. Okay, so here what I'm going to do is I'm going to have this matrix A, which has as many rows as there are perceptrons, and columns as many as dimensions. So right now I just have 1 row, 2 columns, because in the example that I'm looking at, my input is 2 dimensions, but I only have 1 perceptron. So 1 row for the 1 perceptron, 2 columns for each dimension. I'm also going to keep a matrix B, which is just a flat matrix. Actually, you know what? I'll make it a column matrix. So I'll say, same thing, it has as many rows as there are perceptrons. And it just has 1 column, because we only have 1 bias per perceptron. Okay. Let me make sure my code didn't break. All right, so it's still working. Now what I'm going to do is add an additional perceptron. So right now I'm just using random weights, but I want to show you what this looks like in the picture. Okay, so now I can actually represent 2 lines, because I have 2 rows in this A matrix and 2 rows in the B matrix. That would be like going along here and repeating. Actually, I'll go down, just for this example, down to 2 inputs, because that's all I have. But that would be like repeating this picture. and creating another neuron of sorts. And so now, just to differentiate the two, what I'll do is I'll say this is A00 and this is A01. So these are the weights of the first neuron, first perceptron, and then these are the weights of the second perceptron there. And then this would be B0 and B1. I'm not going to even specify the column because there's only one column. Okay, and I guess I'll call this output Y0 and this output Y1. So that's what's happening here in this matrix that I've set up. And then what I can do is actually take those outputs, and there's a number of things I can do with them. Right now, what I'm doing is I'm just summing them together. So I'm just taking the output of each of these neurons, and I'm summing it together. Oops, let me get back my Y there. So I'm just going to feed the output of each of these into like a plus operation. And then my final output is going to be the sum of those two. And I guess I'll call that Y. Okay. And so now I could do something more complicated than just linear separability. I can actually have the interaction of these two neurons working together. And so I can make more complicated regions. Now, just to get a handle on how do I actually move these lines around, it's good to know that so these weights actually taken together, they represent the normal, so the direction that's perpendicular to the line, and then the bias actually represents distance from the origin. So with this interpretation, let's actually go in and plan a little bit about what lines we would like to place down to enclose this region inside, because that's something we'll be able to do now, because we can actually have multiple lines working together. So I'll start with an approximation of this, which is just going to be some lines that make roughly some kind of square or rectangle around this. And I'll think about, what is the perpendicular to those lines there, or otherwise the normal. So for this one on the left here, the perpendicular would have coordinates -1, 0. For the one on the other side, it would be the opposite of that. It would be 1, 0. So on this side, we've got 1, 0. That's the vector that points away from this, because we want it to grow in that direction. We want it to be a larger number. And then up here, I've got this pointing up at, let me rotate this 90 degrees counterclockwise, because that is going to point up 0, 1. And then of course the one on the other side is going to point 0, -1. All right, so let's try to start with those, and we'll have to move them away from the origin a little bit, so they all should have a bias. So let me go back to the code here. I actually set up the matrices myself. Okay, so the first perceptron should have weights -1, 0. So basically ignoring the Y coordinate, which makes sense, right? Because it only is actually sensitive to X. Then I'll do this one, 0, -1. And then 1, 0, and then 0, 1. And I'll give each of these a bias of some amount here. So maybe 1, 1, 1, 1. I'll make them all bias 1. Let's see how we did. Okay, and actually the other thing I need to think about here is the threshold is no longer going to be 0.5, because these are actually working together. Actually, it looks like I got this the opposite way too, which is interesting. I think I actually want these slopes to be flipped around. Oh, no, I just want the biases to go the other way. That's it. Okay. Okay, anyway, yeah, so this is more like what I was shooting for. Actually, it looks pretty darn good. The thing I have to change is that what is the cutoff? It's no longer 0.5 because I have 4 things added together. Let's make it around 1.3. It looks like. Okay, maybe 1.2. Wow, good. We got it spot on. So yeah, with 4 neurons we can get it. Actually, we could probably do a triangle too. The triangle. So 3 neurons is probably the least that we could do to get this here. All right. So that is how we get multiple perceptrons to work together. There's a really nice tool that actually demonstrates this idea that was created by TensorFlow project out of Google, and they show how you can start with some inputs. So here I have a very similar data set to the one I just showed you. It has 2 coordinates. And I can choose, actually I'll do what I just did. I can choose to have 4 neurons there, and then I can click the play button. And eventually they'll work together to learn something that fits this very well. And like I said, I can actually get away with just 3. Let's look at that. Whoops, I didn't mean to do that. We're going to have 3 neurons here. And you see what each one learns here, right? So they each learn that little half space. So each one individually can only linearly separate, but together they actually carved out this little sort of rounded triangular region. Okay, so that's cool. One thing I want to point out here actually is that there's a few different ways. So we talked about, they call it the sigmoid here, but this is the activation function we were using. Actually, it ended up not working quite as well. It took a little longer, but it got there eventually. So that's you know, this little thing that I drew up here, that shape that we talked about, the logistic function. But there are other activation functions that you can use. A very common one is called ReLU, Rectified Linear Unit. And let's see, is it able to learn with this one? Looks like it got stuck actually. Let's see if it does a little better with 4 neuron. Okay, I actually did that one pretty quick. So yeah, Rectified Linear Unit looks like basically a line, except so it's called a ReLU for short. So let's maybe look at it just from -2 to 2. And so the ReLU, it's going to be U. It's going to look like a line, except when you're less than 0, you clamp it to 0. So if I were to plot this here, it looks like this. So it also has the property that it doesn't fire. It doesn't sort of give you anything positive until your input to it is greater than 0. But then it saturates completely in the negative region. So actually, this is not differentiable either, like the perfect step function. But unlike the step function, it doesn't have a jump discontinuity, so it's not quite as bad. There's just one point that you can't differentiate it. So people actually found that this was pretty useful. Another kind of slightly modified version of this is, well, you can actually, this is called the modified, or the leaky ReLU. So what I could do is say, okay, I'm gonna, you know, it's not going to be 0 all the way, but it's going to have a much smaller slope to the left of the origin. So that's one thing I can vary here. So I don't have to use this logistic function all the time. I can use something else. Another thing I can do is I can actually keep adding layers to this. So what I mean is you know, the outputs of each of these neurons. Before I just said, oh, I'm just going to add them right together, right? But you could actually pretend that the outputs of these neurons are the inputs to another set of neurons. And so here, the outputs of each of these 4 neurons each became 4 inputs to 2 other neurons, or I could choose more. And what people found, actually, about a decade ago, there was a resurgence in work using neural networks. What people found is if you make these deep, so if you have a lot of layers, then it can learn better, and it can learn more complicated things. It's a little bit harder to interpret exactly what these inner layers are doing. So these are called the hidden layers, by the way. So the first layer is the input, and then this is the first hidden layer, second hidden layer, third hidden layer, fourth hidden layer, and then we have the output. So it's a little bit hard to understand exactly what the hidden layers are doing. But, you know, it was much easier to interpret the first layers here. It was just, you know, separating over a line. But they're very useful. Okay. So that's basically it with neural networks. That's all they are. You just bunch of logistic functions and you link them together in this way. So the outputs of logistic functions become the inputs to ones that follow them. and there's geometric interpretations at every level. But once it gets deeper, it's gotten a little bit harder to follow everything. So they end up being kind of mysterious how they actually work in practice. But I'll try to give you some tools to understand what they're doing. Okay, so now I'm just going to have you do a little exercise. I put some notes here to put together everything. You know, I actually showed like one layer going to the next, so inputs here going into different neurons, and I explained how I showed how we can interpret this as a matrix, which I've already done, right? Or I guess I called it A up here. I should call it W. That's what I called it before. So yeah, I've got my matrix of weights. It has as many columns as there are inputs, and it has as many rows as there are outputs. And that's a good way to describe this. And then you have this matrix for the biases. So just got some notes about that. And then, to see what the neural network is going to do, I haven't explained how to train it, but if it's been trained, so if I have these weights, I kind of selected them by hand here. If I have these weights, the way that you evaluate it is you just keep doing matrix multiplications. You add the bias, and then you feed all those outputs to that nonlinear function, whether it's the logistic function or the ReLU or the leaky ReLU, or there's some other options here like the hyperbolic tangent, tanh. So I don't know, people find in practice certain of these work better than others in certain applications. All right, so I'll have you do a little exercise coding up this algorithm to evaluate a neural net, and then we'll continue and I'll show you how to train them.